For some reason, there's words on the bottom that says type something. What are we going to type? Chemical. Doesn't even work. Did I press the wrong button? No, thank you. Please don't say that even. Okay, that's gone. Okay, physical science time. Let's talk today about, we're going to talk about chemical bonding. Shh. Chemical bonding. Naming. And writing. Please stop that. Formulae. Please stop. Who? What shiny? Oh, it's Cyrus's chair. I thought someone was intentionally shining a shiny on me. But it's just Cyrus's chair. Okay, well. Is this mic picking up? Yeah, okay. Chemical bonding, naming, and writing formulae. The correct pluralization of the word formula is formulae with an E at the end of it. But formulas will also be used interchangeably, even though it's strong. It's accepted in English. I think actually probably in most, I don't know, peer-reviewed upper-level papers probably would even say formulas. But the correct Latin pluralization is formulae with, like, just the word formula with an E at the end, and the verb conjunction A-E sounds to E. Okay, you don't care. Let's define each of these things as we're used to doing. I hope that didn't stop the video. Let's define each of these things. We have talked quite extensively about chemical bonding already. When does chemical bonding occur? Why does chemical bonding occur? Let's start with why. Yeah, the octet rule says that I'm just going to put all elements except two. Which two? I don't want to use that word. Are most stable with 8 valence electrons. Which options? No, which two elements aren't most stable with 8? I'll give you another hint. These two instead are most stable with 2 valence electrons. Okay, I'll give you another hint. One of them is helium, which has 2 valence electrons. What might the other one be? Hydrogen. Yeah, how did you guess that? Is this just a wild guess? No, because both hydrogen and helium only have 1 electron orbital, which is also technically their valence orbital, and that first orbital only ever holds valence electrons. So all elements are most stable with 8 valence electrons. I guess technically, lithium and beryllium are also more stable with 2 valence electrons, and even boron. The point of this is that even though it's called the octet rule, which relates to the number 8, like octopus or octomom, it's saying that they're most stable with 8. But really, they're most stable with a full valence electron shell, which for most of them would be 8, but for others could be the lowest valence shell, which is 2. Anyway, and how do they get this way? Okay, so let's say you are most stable when you have $8, and you happen to have 10. You get $8 instead of 10. You could spin 2. Could you just throw $2 on the ground and it would be, yeah, of course you could. But an atom can't. An atom can't just get rid of or just manifest electrons. Atoms, let's write this down. Atoms cannot, I guess we could just say create or destroy electrons. They can, and these are the things they can do to get 8 if they don't already have 8. They can do what? We're going to list 3 verbs. They could share. We're going to name that in a second. What else could they do? Give, yep. Or take. And these verbs give and take imply that something else is involved. What else must be involved? This is actually one of the standards. What else must be involved for sharing, a giving, or a taking? So another atom, these have to have at least one other atom. What do we call it if they have, what kind of bond is formed if they share? Covalent. What kind of bond is formed if they either give or take and then they're held together by their mutual electromagnetic attraction? Ionic. Good. And that's from the last chapter. So what's more stable? Well, they're both hydrogen. Which one's more stable, though? The H2, yeah, it has bonded with another hydrogen to become more stable. Which one is more stable? H2O. It has bonded with these two other hydrogens to become more stable. That's why they do this. Why do they bond? Why do they form compounds? These two are both compounds. The compounds generally, almost always, not always, but almost always, the compounds are more stable, or we should say they're more stable under a given set of circumstances than just the elements that make it up. That's why they do this. To achieve stability. That's the simplest word. Why? To achieve stability. Wouldn't that be nice? Okay. To achieve stability. What does the formula tell us? We've had this discussion before, but let's just review. What does the formula tell us? What does this H2 or H2O tell us? It tells us the ratio. It tells us how many of each kind of atom there is. This little subscript here tells you how many the atom that goes before that has. Think of the subscript as going with the one to its left. Good on all that? This should be review. I can't, to be truthful, because it's been several weeks since we talked about it, I can't remember if this was in the previous video or if we had just talked about it since then. But anyway, this should all be a review. We have definitely talked about in class all of this stuff, right? Does anyone have questions about this before we move on? Colton? What question do you have? Good. Try to think. Good. Okay, if you do need, and this goes for anyone, not just Colton, if you do need extra review since we were off for a week, that is perfectly acceptable. Please talk with your friends first and talk with me if you both can't figure it out. And also we will do some chapter reviews that will help, well, obviously review. That's the whole point of a chapter review. Okay, so let's go on to naming and writing formulas. So this should have been review about why chemical bonding occurs, and now we're going on to naming and writing formulas. We'll do it in the opposite order. Let's say I have, let's just do some easy ones. I'll draw a diagram of the element lithium and a diagram of the element fluorine. Now I'm going to draw just its nucleus, and we're going to draw its its electrons. So in lithium, what's in the nucleus? Let's say it's lithium-6. What's in the nucleus? Yeah, there's protons and neutrons. Anyway, it has a positive charge. In lithium-6, it would be 3 protons and 3 neutrons. You remember that? But for now, we're just going to draw that it has a positive charge in the nucleus. How many electrons can we sometimes call orbital, but probably should call energy levels? How many can be? 2. 2. So, thank you, Cyrus. So there are 2 electrons in the first energy level. How many does lithium have altogether, and how do I know? An atom of lithium has how many electrons? It has 3, so how many should be in the outermost, in the valence electron orbital? 1. Good. So how many valence lithium have? No. 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 How many valence electrons does lithium have? 1. So its electron dot diagram looks like that. Let's do fluorine now. Has a nucleus in the middle. How many in the first level? Nope, in the first level can only have 2. So it does. It has 2. And then the next level, Tatum, has 1, 2, 3, 4, 5, 6, 7. How many can the second level have altogether? How many can it have? It can have 8. Remember, the outermost can always only have 8. 1, 2, 3, 4, 5, 6, 7. In this case, the fluorine has 7 valence electrons. So just looking at these two things, and I picked them for a reason, how do you reckon these will bond and why? First of all, why? Why will these two things bond? What does lithium have? How many valence electrons? 1. What's it most stable with? 8, or it's most stable with a full shell of valence electrons. How many does fluorine have? 7. How many is it most stable with? 8. So there's a pretty easy looking thing here. What could happen? They can't share. They can't share because fluorine wants them too bad. Say it again. Ionic bond, yeah. So the lithium's 1 valence electron, it's going to give that to the fluorine, which it's happy to do because now it's more stable with 2. It has 2 in the next shell down. And the fluorine is most stable because it has 8 in its outermost shell. But lithium now is not, it's not lithium, it's lithium what? It's a lithium ion, so it's lithium plus, and this is fluorine minus. Why is lithium plus even though it lost an electron? because electrons have a negative charge, and so if it lost an electron, positive charge. Fluorine has a negative charge. What do we know about positive and negative? Opposites attract. There's an ionic bond. Does this happen? Well, what's the ratio here? How many lithiums, in other words, does it take to make the fluorine stable? 1. So the ratio is 1 to 1. So the compound is called, or the compound looks like this, LiF, and it's called lithium. We just say the name of the positive ion, and then we change the name of the negative ion to end with "ide." So lithium fluoride. Instead of fluorine, it's now fluoride. That's your first naming rule. Let's write that down. In ionic bonds, the first naming rule is name the cation and then change the suffix of the anion to "ide." So for instance, if it's fluorine, fluoride. If it's oxygen, oxide. If it's sulfur, it becomes sulfide, etc., etc. Name the cation. Hey, have we heard of these things before? Let's define these. What's a cation? Well, can you guess just from context here? True of this, the lithium. How do we know whether it's a cation or an anion? And what do those things mean? What is different about them? They're symbols. No. They're what? They're charged. Yep. The positive one is called a cation, and the negative one is called an anion. I don't know if any of you work on like car batteries, but you might be aware that batteries have a cathode and an anode, which is the positive and negative terminals, and that's related to this. But the way I remember it, or the way I remembered it back when I had to remember, is that cat is happy, positive, even though I don't really like cats. Look how cute he is, though. He's happy and positive. And onion, stinky, negative. Bad. Draw some stink lines. I actually do like onions. So one way you can remember it is that onions are good but negative, and cats are bad but positive. No, if you like cats, this will work easier for you. Especially if you like cats and don't like onions. Who likes cats? That's okay. You don't have to be embarrassed. Who likes cats? Who dislikes onions? Jaden, this is a great mnemonic for you. Just imagine that you're Jaden. You want to assume that you're Jaden. Maybe put on a piece of Jaden's clothing, and then you can pretend to be Jaden, and then you can think to yourself, cations are positive. Let's write that down at least. Cations are positive, and anions are negative. We always list the cation first, and then the anion, but we change the name to "ide." Okay? So let's do another one. What if we had this? What if we had sodium and oxygen? What if we had sodium and oxygen? Okay, let's say if we had sodium and oxygen. Well, where's sodium at on the periodic table? This is how we actually do this. Where's sodium at? What group is it in? No. First. It's in the first group. It's in the alkali metals. And so how many valence electrons does it have? 1. It has 1 valence electron. So what will its charge be when it bonds? And try again. Positive 1. It's going to lose that 1. Oxygen. Where's oxygen at? It's in group 6. So it has how many valence electrons? 6. It has 6. How many does it want? 8. So how many is it going to gain? So what's its charge? Negative 2. Negative 2. So how are these going to bond? Well, in this one, the 1 plus and the 1 minus just bonded 1 to 1. But how will this bond? They will bond. It's 2 sodiums to 1 oxygen. Why? Well, the charges have to add to 0. Charges add to 0. And what can we adjust to make the charges add to 0? What thingies do we change to make? What did I change about these when I stuck them together? I added I put it in what's the name of it? Subscript. The whole thing, you're right, Tatum, this whole thing is called a formula. And what I've just done is writing a formula. But all I can change are the subscripts. And I have to change them so they add up to 0. Yes? Does everyone understand that? So now let's name this. What is the name of this? I already told you. Sodium. Sodium oxide. Sodium oxide. We don't say the is its name. So that's that's a pretty simple example of writing a formula and saying a name. Usually you'll be given one or the other. Colton, if we want to go. So let's try another one. Name it. This is something like, this might be on your worksheet. Number 1, what is it? This. Strontium fluoride. All right, the formula. Yeah, you're looking in the right spot. You look at the periodic table to find what? What are you looking for? SR, good. Make sure you do capital S, lowercase r. F. Do I need to change the symbols? I don't mean symbols. Do I need to change the subscripts? No, and how do you know? Oh, you do need to change the symbols, actually. Yeah, where's strontium at? How many valence electrons does it have? It has 2. And how many does fluorine have? No. 7. So what's my ratio going to have to be? Nope. How many fluorines is it going to take to make the strontium happy? How many valence electrons? No, try again. You know this. How many valence electrons does each fluorine want to gain? It wants to gain 1, right? So if each one wants to gain 1, and strontium has 2, how many fluorines is it going to take? Dose, yeah. Imagine, trying to think of a way to make this appropriate. Imagine that you're a dude who's got 2 ice cream cones, but you don't like ice cream, so you have to share it with some chicks, and each chick only wants 1 ice cream cone, so you have to give 1 to 2 different chicks. Do you understand what I'm saying? That's just like this. The strontium has 2 ice cream cones, but he doesn't want any, or rather he has like 8 inside of himself, but he only wants those. I don't know. The metaphor is getting a little bit complicated, but 2 ice cream cones. Each chick, the fluorines, only want 1 ice cream cone, so each one can only take 1. So it takes 2 chicks to make strontium happy, okay? Chick is an offensive word. Do not use it. Pretend I said puppy dog. Yes, exactly right. Okay, so obviously, which of these was more difficult? Naming it or writing the formula? Just writing the formula by a little bit. You just have to get good at it. You just need practice, okay? Let's complicate things. Okay, so now what can happen is that we also have, look on page 619. Everyone open your books to page 619. I'm going to show it to the camera. If you're watching this, maybe if you're downstairs and you don't have any choice but to watch this, you could pause it here so you can see them. On page 619, there's this little chart of polyatomic ions. Did that show up the right thing? This. I want to show this. This. Yeah, okay. There's a chart of polyatomic ions. Let's write these down. So what do you notice about the polyatomic ions? Polyatomic ions. Yeah, they have more than one kind of atom. They're poly. What's the prefix poly mean? It means many. Atomic, so many kinds of atoms in one ion. So we used the cation or the anion, except now they have their own little self-contained charge. So let's say instead of strontium fluoride, I now have strontium sulfate. Well, okay, here's a clue. If you see that what did I say that these ionic bonds, what does the suffix have to say if we're using just an element? "-ide." But this says sulfate. Do you see that? Sulfate. So what does that tell me? Is this just an atom? Is it sulfur? No. It's a polyatomic ion. So if you see that it ends in "ate" or "ite," it must be a polyatomic ion. Now listen, not all the polyatomic ions end in "ate" or "ite, so you kind of just have to know this chart, and you'll get better at it as you go along. But this one is definitely a polyatomic ion. So is it strontium sulfate? So what's the symbol for strontium? Did that change? No. R. Now look on the chart. What's sulfate? No, look on the chart. That's not up there. Look on the chart. Your polyatomic ion chart on page 619 in the top right corner. SO4. And its charge is -2. What was the charge on the strontium? Do you remember? Positive, no, try again. +2. And so if that's +2, and this is -2, do I need to change the number? Nope, the ratio is just 1 to 1. Strontium sulfate. Okay? Now, okay, one more. Yes, go on. So what if you do need to change the number? Is that what you're going to ask, Rhett? Oh, I wish you were. Someone ask that, please.
Sure, what if you were to change?
Great question, Justice, but what is your question, Rhett?
So, how do you know if it's positive or negative?
On the polyatomic ions?
Yeah.
It tells you. The chart.
Like just
Oh.
in a normal compound.
The positive one always comes first. Remember, that was one of our rules, is that the cation has to come first. So like, you mean which one of these is positive and which one's negative? The strontium must be positive because it comes first.
How do you know which one comes first?
Like, well, the name is the same too. And even in the name and in the formula, the positive one has to come first.
What if you had to build the formula?
You won't. You might, like for instance, if you had like, in this one up here where I showed you that we had sodium, or maybe the lithium that I just literally erased, where you just have the thing and you have to diagram it, you'll see one only has 1 or 2 valence electrons and the other one has 6 or 7. See which one has to gain and which one has to lose. Okay. Let's talk about now, let's say we have sodium carbonate. Sodium carbonate. Well, once again, what's the 8 tell us? What's that a clue for? Polyatomic ion. Something's going to be a polyatomic ion. Na is sodium, still. What's carbonate? CO3. But, check it out. What's the charge on the carbonate? -2. What's the charge on the sodium? +1, because it's in group 1. So what do I need to change? Sodium is +1. You can put these in as little helpers if you need to. Remember, I can only ever multiply. Yeah, I need by 2. And then those are just little. You can use them as bookkeeping things, but I wouldn't keep them. That's another thing, is that these have charges when they're given to you, but the charge transfers to the sodium. You don't need to write. Now, the last example I'm going to give is this one for these ionic ones, because it can confuse people. Calcium, let's put this, calcium acetate. Well, what's calcium? Ca. What's acetate? What's the look at your chart. Remember, 8 means polyatomic ion. So what's acetate? H3O2. And its charge is -1. It's -1. If it just says negative, that means -1. So it's -1. What's the charge on the calcium? Look at it on the periodic table. It's not negative anything. +2. Calcium's +2. So if the calcium's +2 and the acetate is -1, what do we have to do? We don't add. We multiply what by 2? The whole acetate. So what we have to do is we group it. Just like in math, you put parentheses around it to show that this 2 applies to the whole thing, just like in math, okay? So write that down, because someone's going to forget this. So if you have a polyatomic ion, polyatomic ions must be in parentheses only if they have a subscript. Like if you need to multiply the number, I'm going to put that, if they need to be multiplied, because that makes more sense. If they need multiplied. So do you always put parentheses around it? No, we didn't for sodium carbonate. Only if we need to multiply it. And all of this was for what kind of bonding? Ionic. Everything here was ionic bonding. Covalent is quite a lot easier. Let's do that real quick before we have to go. The covalent is quite a lot easier. And we will just, if you have questions as we go along that are pressing, like I don't understand this at all, please, you need to ask them. But otherwise, we will do this when we practice them tomorrow. I just want so that you can watch this video and have some practice. You may move over here where it's cool in the woods. Anyway, for covalent naming and formulas, there's a list. If 2, 3, 4, 5, 6, 7, 8, 9 on the bottom. However many there are, each one has its own little prefix. 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, and 9 is nona. And we just put these prefixes to match however many there are. What kind of atoms are joined together in a covalent bond? You remember? Ionic, it was always a metal and a non-metal. But in covalent, what must it be? I asked what kind of atoms are bonded in a covalent bond? In ionic, it was a metal and a non-metal, metal and a non-metal. But in covalent, it's always, not always gases, but it's always non-metals, always non-metals. For instance, we might have, in a covalent bond, we might have N2O. How many nitrogens are there? 2, so we call it dinitrogen. How many oxygens are there? 1, so we call it monoxide. You kind of drop the last vowel here if the thing begins with a vowel, which is oxygen. If it begins with oxygen, you kind of drop the last vowel. So dinitrogen monoxide is what you have that. What about this one? CO2. You already know what this is. Now you know why it's named this. What is it? What is it? Carbon. We don't have to say the mono all the time. In fact, we usually drop the mono unless it's specifying that this is different from another one. Anyway, carbon, what? Dioxide. But because it's specifying that it's not carbon dioxide, what's this one? Carbon monoxide. We usually, once again, we usually don't put the mono unless it's differentiating between that substance and another one, which you kind of have to feel out. In fact, I would say generally don't put the mono unless you know that you should. The one that's kind of like this that does have a NO2 would be nitrogen dioxide. Nitrogen dioxide. That's kind of like a flimsy rule. Like, you just kind of use the mono sometimes, but not all the time. Carbon monoxide is super poisonous. Yep. You can see just by the difference between carbon dioxide is not good for the planet, but it's not poisonous to your body. Just in the difference between these, why might this sometimes come up? When did this happen? You know? Okay, yeah, it's less stable, but it's also, it occurs when carbon dioxide is normally produced, but there's not enough oxygen. So like sometimes people's inefficient furnace, or like the engine in your car, produce carbon monoxide, which is poisonous.
That's why they don't want to start the car with your garage.
Definitely don't start the car with your garage open unless you're trying to die, but please don't do that. Okay, so this is how we name covalent. Could we also take one of these and name it? Well, let's try. P2O5. What would we call that? Hold on, not just because there are 2 of them. Diphosphorus. Yep, pentoxide. You just stick this means how many number? You just stick the number of it with the name of it. And you go in the same order. This is technically set up in this way too. They're not, or positive 1 goes first, but don't worry about that because these will just be in the same order as what you write. Or the name will be in the same order as the formula. We do still change the end of the last one to "-ide". You need more practice on this? You need more practice on this. But other than that, I mean, this is all the information for naming. We do have one other thing to cover, but we'll do that when we get to your worksheet. But this is all the information. All you have to do now is work with it until you're good at it. So basically, I would say, if you know your vocabulary, that would be a great plus. Know the vocab, know the concepts behind why chemical bonding occurs and kind of how it happens. Review those lesson assessments that we did. And then this is the main thing you're going to be doing. Like instead of a math page, you're going to have a naming and writing formulas page, which will be more than half your test. Okay, you just need to practice. Do you have questions? Do you think there's a question you could ask that might help Peyton? Yes?
No, not.
Okay, well, okay. Do you have any questions that would not help Peyton or might even make it worse? Justice, go ahead.
What's number 5?
5 is penta. Penta. Sometimes we use this in geometry even. You know about triangle. Many of these, like, you've heard of almost all of these because these are like prefixes for shapes. This is because these are the Greek prefixes for numbers. Even try, you do. Tetra, how can we remember tetra? That's the only one that doesn't really fit or that you don't know about. Tetra, tetris. Yeah, all the little tetrises, little things in Tetris, all of them have 4 little blocks. That's how I remembered it when I first did this. Tetra, think about Tetris. Tetra is 4. Questions?